So today we're going to be talking about rotational energy, which is going to be our third lesson on rotational motion. So consider a mass m on the end of a string that's being spun around in a circle with radius r and an angular velocity omega. So let's take a look at this from a linear point of view. And then we'll translate that into rotational. So we know that the linear velocity is equal to the angular velocity times the radius, and from all of our work on linear motion earlier, we know that for an object that's moving, its kinetic energy is equal to 1/2 times the mass of the object times its velocity squared. So here we got two equations, we can go ahead and glue them together, and what we end up with is a mess. So we got that energy kinetic is equal to 1/2 the mass times the angular velocity times the radius, and all of that squared. So this isn't very useful to us until we remember that for an object that's spinning, that has all of its mass moving on the outside, the moment of inertia for an object like that is equal to the mass times the radius squared. Now, we can do a little bit of factoring, a little bit of combining, a little bit of math, and what we end up with is the equation for rotational kinetic energy that we're going to be using. So that's going to be equal to 1/2 times that moment of inertia times the angular velocity squared, or kinetic energy rotational is equal to 1/2 I omega squared. So let's, if you'll pardon the pun, put this to work. So a 35 kilogram grindstone with a radius of 0.61 meters is being used to sharpen an axe. The outer edge is moving at 1.5 meters per second, and we want to figure out how much work was required to get up to speed. So work in this case, we're just going to use that as our change in energy. So all we have to do here is find the end kinetic energy of this rotating object, and we just found the equation that we need to do that. So that's going to be that rotational kinetic energy is equal to 1/2 I omega squared. So let's split that up into its parts. So that kinetic energy is going to be our work, and that's going to be 1/2 times that moment of inertia. This grindstone is basically acting like a cylinder. So I got the moment of inertia equation for a cylinder in there. That's 1/2 times the mass times the radius squared. And then we're going to multiply that by the angular velocity, which is the linear velocity over the radius. And since that's squared, both of those are squared as well. Now, you probably noticed that we've got a radius in the denominator and a radius in the numerator, so we can go ahead and cancel those out. And when we go ahead and combine those fractions, what we end up with is something that looks pretty simple. And that's a theme that we're going to see is lots of times things are going to cancel, things are going to combine. So if you go from a complicated equation to an easy equation, that doesn't mean that you've done something wrong. In fact, most of the time, that means you're doing it right. So from here, let's go ahead and plug some numbers in. So that's going to be 1/4, 35 kilograms times 1.5 meters per second, and all of that squared. So this gives us an answer of just shy of 20 joules of rotational energy. So this is for an object that is sitting still and rotating. However, there's going to be lots of objects that we deal with that are rolling. So let's talk about those. So when you have a rolling object like this, you've got two kinds of motion. So it's both moving and spinning. So the center of mass is moving translationally. So that means it's moving along the axis that it's moving along, and you get to pick that axis. So x-axis is usually a good one to choose. And then the whole rest of the object is spinning. It's undergoing rotational motion. So a couple of things. One is the very top of the tire is moving at twice the velocity of the middle, and then the bottom of the tire isn't moving at all. Pay attention to the words that are coming out of my mouth rather than the words that are up on the screen. So, top of the tire is moving at twice the speed of the middle, and the bottom of the tire isn't moving at all relative to the ground. So, this means that when we've got something rolling, we've got two different kinds of energy here. So we've got both rotational kinetic energy and translational kinetic energy. So putting that in an equation, that total kinetic energy is equal to the translational kinetic energy that we've come to know and love, and the rotational kinetic energy. So we can also break that apart into its parts, and we end up with that energy kinetic total is equal to 1/2 mv squared plus 1/2 I omega squared. And that does look like a mess. However, we'll see that just like in the previous problem, lots of things are going to end up canceling and combining in order to make this easier for us. So let's go ahead and do an example with this. Or first, rather, let's talk about what that means. So here we have a ball released from rest on a no-slip surface. So that is meaning that it's going to be rotating just fine. Upon reaching the lowest point, it's going to hit a frictionless surface, and it's going to come back up the other side. So what does that mean as far as the maximum height goes? And this is a common problem that you might end up seeing on an AP style question. So here we have something that's starting up on this side, on the part that's going to make it start rotating, and then as soon as it gets to the bottom, that rotational energy isn't going to change, so it's going to maintain its current motion. And that means that it's going to end up with a lower height because it's going to keep spinning up on the far side, and that energy, which was gravitational over here, is still going to be hung up in rotational motion over here. So we're not going to get as much gravitational energy on the far side. So in this problem, a bowling ball that has a radius of 11 centimeters and a mass of 7.2 kilograms is rolling without slipping. So basically, this just tells us that the linear velocity and the angular velocity are related the way that we want them to be. At 2 meters per second on a horizontal ball return, it then continues to roll without slipping up the hill to a height of h before momentarily coming to a stop and then rolling back down the hill. So model the bowling ball as a uniform sphere and then calculate the h. So let's go ahead and do that. So what we've got is an energy problem. So here we've got that gravitational potential energy is going to equal our translational kinetic energy plus that rotational kinetic energy. So let's go ahead and split that apart into all of its components. So we've got our equation for gravitational energy of mgh, and that's going to be equal to 1/2 mv squared, so that's our kinetic energy, plus 1/2 I omega squared, and that's our rotational energy. So let's, similar to what we did on the axe problem, split that moment of inertia and that angular velocity into its components. So it's getting worse and worse and messier, but we can still handle this. So mgh equals 1/2 mv squared, that hasn't changed, plus 1/2 times that moment of inertia for a sphere, which is 2/5 mr squared, times the velocity squared over the radius squared. So remember how back then I said that you don't have to worry about things canceling out? That's going to be a huge advantage in dealing with very ugly problems like this, because you can probably notice that all of those masses end up going away, and those radii go away as well. So from here, we just have to deal with the fractions. So let's go ahead and rewrite this, and what we end up with is g times h is equal to 7/10 v squared. So the difference here is in that fraction. If we were only dealing with the linear velocity, we'd end up with a 1/2. So now, because it's spinning and we're taking into effect that rotational motion of the ball, we're dealing with 7/10 instead. So it's going to be going up the ramp a little bit higher. So let's go ahead and solve for h. So h is going to equal 7v squared divided by 10 times g. Plug some numbers in there, and what we end up with is 0.29 meters. So again, that moment of inertia of the ball and the rotational motion of the ball ended up changing how high that ball ends up going up the ramp. And in a lot of problems that you're going to be running into, you're going to see how the shape of the object affects how it moves. In fact, one of the problems that you're going to be dealing with in this section's problem set is going to be looking at how shape affects how objects move down a ramp. So you'll be comparing how a sphere, a cylinder, and a hoop all roll down a ramp at different speeds and see which one gets to the bottom quickest. With that, I hope you have a wonderful afternoon, and I will talk to you all later.